Hi, welcome to this lecture on servo motors. So a servo motor is a different type of motor than the DC brush motor we've talked about before. A servo motor is used to do more precise movements and timings. So let's take a look. So servo motors are for precise control of position, velocity, and acceleration. So remember before with a DC brush motor we can control the direction and we can control the speed, but we don't get to control things like position. We can't tell a DC brush motor, for example, turn exactly one revolution and stop. It doesn't really work that way. You'd have to do all sorts of weird details with timings and the load on the motor and things like that. So a DC brush motor is not made to be that precise in that way. A servo motor, on the other hand, is. It's designed to have precise control of a whole bunch of different factors. And the way it does that is it has integrated gear head and control electronics. So inside of a servo motor, you have gears, sensors, control electronics, etc., so that you can tell a servo motor, for example, turn exactly one revolution and stop. You can send it all sorts of precise things you want it to do, and it will do them. It uses pulse width modulation as the control interface. So remember, on a DC brushed motor, we use pulse width modulation to control speed. In this case, it's a control interface to specify to the motor exactly what you want it to do. So a standard servo motor is designed to seek and hold to a specific angle, and it has about 180 degrees of rotation, meaning if I have a motor with an arm attached to it, that arm can swing a total of 180 degrees, which would be about that range. Can't spin all the way around because it doesn't have 360 degrees of rotation, only 180 degrees. And what angle it turns to is controlled by the length of a pulse width modulation pulse. Now, this type of servo motor would frequently be used in things like robotics or other industrial uses where you need to be able to precisely turn to a specific angle. Another type of servo is called a continuous rotation servo. And this is designed to turn at specific speeds, and it can turn the full 360 degrees. So again, if we have a servo motor with an arm attached to it, well, that arm could go the full 360 degrees and keep turning. But how fast it turns is controlled by the length of a pulse width modulation pulse. So remember, a standard servo, the pulse tells it what angle it should go to. A continuous rotation servo, the pulse tells it how fast it should be turning. Now, the interface you use to connect and control a servo motor is, like I said, pulse width modulation. And you control it by sending a pulse with specific widths. And that width should be repeated every 20, and that pulse, I should say, should be repeated every 20 milliseconds. So let's do an example. So for a standard servo motor, you might pull up the data sheet and find that the data sheet says, okay, if you send the servo motor a pulse that's 1.25 milliseconds wide, and you repeat that pulse every 20 milliseconds, then that'll cause the motor to turn to 0 degrees and to lock. If instead you send that motor a pulse of 1.5 milliseconds and you repeat it every 20, then that'll cause the motor to turn to 90 degrees and lock. So the length of the pulse defines exactly what the motor is doing. And likewise, we might find out that 1.75 milliseconds causes the motor to go to 180 degrees and lock. And anything less than 1.25 would probably cause nothing. More than 1.75 would probably cause nothing. But between 1.25 and 1.5, you could imagine that would range all of the degrees between 0 and 90. And from 1.5 to 1.75, you could probably do all the degrees from 90 to 180. So the length of the pulse defines what's going to happen. A continuous rotation servo, on the other hand, might have something like the 1.25 millisecond pulse causes the servo to turn counterclockwise really quickly. A 1.5 millisecond pulse causes it to stop, and a 1.75 millisecond pulse causes it to turn clockwise really quickly. And of course, the time values in between these would cause slower movement in the associated direction. So for example, a 1.6 millisecond pulse might cause it to turn counterclockwise. 1.6 millisecond pulse would cause it to turn clockwise, but not as fast as a 1.75 millisecond pulse, for example. So let's look at a simple example of what I mean when I say these pulses. So let's say that we look at the data sheet and we need a 1.25 millisecond pulse for what we want. We would take that 1.25 millisecond pulse, create it, and then we'd have a 20 millisecond delay where we do nothing, and then we'd send the pulse again. And we would keep doing that, because if you don't keep sending the pulse, the control pulse, then the motor will probably just unlock or disconnect from whatever it is you're telling it to do. So you need to choose what you want it to be doing at that moment. You need to continually send the pulses every 20 milliseconds to send the control. You can't just send one pulse and stop. They have to be sent continuously. So how do we generate the pulses? Well, the microcontroller is really commonly used because it's really easy using a microcontroller to generate the right pulse and the right delays in between. But you could also use a 555 timer to generate pulses like that. You have the equations. You could just configure your 555 timer with the right resistors and capacitors to generate the right pulses. Let's make I want to make a few observations or notes on this pulse width modulation interface. The exact timings will vary from servo motor to servo motor. So you need to check the data sheet for your device. There are some basic standards, but they're not all exactly the same. So check the data sheet to figure out how long your pulses should be for what you want. Remember that the pulses need to be repeated about every 20 milliseconds. Servos are surprisingly forgiving though, so if it ends up being 25 milliseconds or every 15, it's probably not going to matter. But 20 tends to be the universal standard. If you stop sending pulses, the motor will stop running. And the accuracy of the pulses is very important. There's a difference between a 1.5 millisecond pulse and a 1.55 millisecond pulse. If it's a standard servo, this one would turn a little bit farther. If it's a continuous rotation servo, this one would spin a little bit faster. So the accuracy of the pulses is really important. So let's review. Servo motors are controlled by specific timing pulses. Specifically, we use pulse width modulation. You need to check the data sheet to get the exact pulses for your motor, or interestingly, you could just experiment. If you have a microcontroller, you could write a simple program to try different pulse lengths to see what the motor does, and you could probably figure out the two extremes of the lower and higher end. Pulses can also be generated with a microcontroller or a 555 timer. Your choice. So you could use either one. You could probably use other techniques as well, but those are the two easiest ones. Thanks.